Good afternoon, everyone. Yeah, very nice to be here. Actually, first I have to apologize. I've been given the honor as the fellow for the Institute on the Environment, but I didn't involve too much from my aspect in terms of the previous activities. So, but the support, basically the kind of support I got from this fellowship, I think turns out very productive. You can see really lead me to his special attention to make nanotechnology be useful for environmental monitoring. So that's the story I want to share with you. And you can see here, this is my building, Keller Hall, and the side of Keller Hall, right? So my office is all the way up to 6th floor from here. There's, and then also my lab is there, and a very large lab, almost half of that the areas in is the 6th floor. So so we do a lot of materials device based research there, and so everyone welcome to visit my lab and talk to my student. And yeah. Okay, so this seems not working well. Oh, it's not working well. Oh, now it's working. So. Yeah, you can. Okay. Oh, now it's working. Okay, good. Thank you. Thank you very much. Yeah. Okay, here we are. So this device we are building almost there. So if you visit my lab, you can see this is the one. Okay. Hope that works. Is to show you, in principle, show you we have a device here. It's a tiny sensors and with reaction well, and yeah, it's not working well here. Anyway, no. Okay, I will skip this one. But basically, this is a handheld device, and then if we have a droplet of waters, for example, just as small as 4 microliters, okay, just a droplet of waters, and then you put into this reaction well, and then we have the sensors, a lot of sensors integrated here, and then you plug this in to this handheld device. So final goal we having is try to make this just directly plug into the cell phone, so basically smartphone like iPhone or Samsung phone. So we are doing that right now. So the device we have right now is still is not cell phone based, but is very close. So you plug in, and then you have all the information being picked up from that display. Okay, cell phone based, basically you build up an app, and then you can show all the data being collected. And those data are the data indicate, okay, the information you really care about, like heavy metals. In principle, we can do that. I will show you, and also different antigens, right? Different small molecules, if you have interest. So in principle, this is a very general platform technology can help us to detect the different antigens, small molecules at the same time, just based on one these samples. Okay. This also can expand into large quantity, multiple small reaction wells. You can detect many samples at one time, but that's for research purposes. So the device we set up for this case is for just for the field usage, right? So for example, you bring to the Lake Minnetonka, and then you detect what in the water really you care about, right? Okay, so I think this should be very familiar to everyone here. I'm still in the learning curve about how to educate or communicate with my students and my collaborators, and pay more attention on those kind of effort. Okay, really appreciate all the good websites and the email, a lot of materials I got from this institute. So For environmental monitoring, I think the key being an engineer, I think is the detection parts, right? There's many other aspects for sure, right? So from engineer aspect or for science engineer aspect, so detection of the contamination is one of the key. And there's many source in terms of the contaminations. So it's just you can read yourself. And I just pick up one example here, right? So in terms of contamination, so that's and how this really seriously influence our daily lives. Okay, so one example I pick up is mercury. Okay, I better stand here. So I already. So this example, I copied this chart from this websites, and then it's very clearly show if mercury being circulated around into the food chains, there's a lot of side effects, right? So that's at least down here, all the side effects. So and then you definitely cannot completely get rid of those, right? So you always just have the bar. You set a bar. What's the high? What's the minimum you can allow to have mercury in waters, right, or in certain environment? So so the bar being set. You look at the data here again, as I cut and paste from the website. In China, that's where I originally come from, right? And so they have different criteria, and this come from Ministry of Environmental Protection of People, Republic of China, and this from Clean Water Act, U.S. And there's different criteria, very interesting. Okay, in terms of surface water, and U.S. is 0.012, and then China is 0.05. It seems they are a little bit loose in terms of criteria. In terms of drinking water, and the U.S. and a little bit loose, right? So this talk about the microgram per liter. Okay. There's many ways to do this right now. You know, there's the agency, there's the U.S., China, everywhere. They have to, you know, tell the people what's the concentrations of the mercury in the waters, or surface water, drinking waters. So. So the three methods basically. This the first one is kind of a spectrometry based one, and limit of detection is 2 microliter per liter. So it's microgram per liter. So there's big errors, and it's kind of using the laser. It's a large wavelength laser beams. And the second one called cold atomic fluorescence spectroscopy. And then the limit can go a little bit low, 0.05, but still is higher than what you know, like U.S. requirement, right, or even China requirement for the drinking water. So it's most used, but the most important part is not portable. So I don't have a picture to show you here, but this is very big machines. The same thing here. This even big machines, okay, and then this go to a lower limit. In terms of concentrations, 0.001. So basically cover the drinking water detections. You can do that well. Really, really expensive and portable. So, and the things I try to promote through you know, the past few years through my research. So I figure out there's a way we can help. Okay, from engineer aspect. Okay, I like the terms. The phrase shared by one of our graduates, who is now, I think, the VP for Metronics, or Sanju, I forgot whether he moved. And he said, being an engineer, the most important part in journey is you feel you help the people, right? Since you work out, you really help the people directly. You can see that. So I work on the magnetic sensings for, you know, different biomarkers, different molecular detections, and then initially, I start from the disease detections, basically cancers, you know, lung cancer, HPV, HIV, those kind of detection. And then step by step, figure out our technology really can be used also for environment monitoring. And the goal is here. So basically, you not just have a lab type of system. Some people bring the samples in the lab, and then do the testing, and then that's typically take a couple of days and the feedback. So that's really not convenient. The goal is we really have portable device and go to any place, the lakes or different sites, and then the people right away can collect the informations and plot the chart and then transfer through the internet to the data centers, and then you can collect all the data, put together, and then try to analyze what's the changes you have or what's the attention you need to pay. Okay, so the key, in order to make this happen, I call this overall is intelligent environment monitoring. It's not happened yet, not happening in any country in the world. So, but the hope U.S. could be the one leading this effort. The key, actually, this not happen is not your problem, it's our problem, it's engineers' problem, okay? It's we don't have that technology ready to allow us to do those testings, okay? Very fast and low cost, and at one time, just a small portion of the samples, you can test almost all the, the molecules or the metals, heavy metals at one time, okay? So that's the goal. So technology being developed very fast. If you look at the smartphones, right? And that's change everything. And then what's the backup of the smartphone? What's the technology, right? Makes this happen. I don't know how many of you ask that question. Actually, it's happened in the 1950s. Start from a transistor. That's the invention of the transistors. Got a couple of Nobel Prize based on transistor invention. Starting from physics, come to the integration, come to applications, like recent one, this for three Nobel Prize winner working on the optical one, right? CCD, they even got Nobel Prize because the CCD, the building block for CCD is CMOS, okay? But they pick up the right application and they change our daily lives. Okay, so, but the CMOS kind of run out of gas. And everyone knows that, right? If you work in the engineer field, you know that. And now people are looking for something beyond the CMOS, right? And then there's a roadmap from the semiconductor consortium, including Intel, IBM, Micron, those big companies, and then they point out, so we need something new beyond CMOS. Okay, so what I'm sharing with you, the reason we can have chance or we have hope to do something, what I list on here is we have some technology being developed can beyond the CMOS. So it's not transistor based, not semiconductor based. What's that? So it's spintronic based, or we call the nanomagnetic plus spintronic based. So basically you have the electrons, and the electron has one feature we already used for 50 years, that is charge. That's we have a cell phone, we have everything here, right? We have a processor, right? We just manipulate the charge, build up transistors, right? And everything built up on top of that, thousands, $1 billion market, right, around the world. But we forgot another feature of electrons, that's a spin. Electron carries a spin. We haven't used that well. So my research based on that, try to add these features and then try to design the device, and then you can see, you start from one, now you have two features. You really open the door, can make things you cannot make before. Okay. This is my group, and so Amanda mentioned, I have a lot of activity on the magnetic particle research. That's more materials based, right? We make the material particles. You will see this is very important for the technology I talk about. And also, we're working on the device that I just mentioned, spintronic based, no longer just pure charge. We involve the spin. Now we can make the device you cannot make before, right? And with unique features, low power, fast. Most important for this project we talk about here is the sensitivities, okay? It's more sensitive than CMOS based. And then you can do a lot of other jobs. That's what the center we have. Talk about processors, talk about memory, even look for future quantum computer, based on this new physics, new device. Here, we talk about using this one, step back a little bit, work on the Earth, and then see whether we can do something real and then can impact our society right away. So that's what I'm sharing with you. The magnetic particle, I don't think it is new to you. However, in terms of make a magnetic nanoparticle, make that smart, make it intelligent, make it in the way multifunction, it's very difficult. Okay, not many group can do this, and fundamentally there is a certain limit if you're using the chemical approach to make magnetic particle. You have a limit in terms of make certain magnetic particle, like a high moment particle, like a high moment particle coated with gold or coated with some other materials, really works for different purpose, right, at the same times. And then there's certain limit. In my lab, we build up what we call the physical deposition system. We can make a particle almost, all kind of particles. For example, here, gold-coated iron cobalt particles. There's so far still no other method can make this. Gold is a golden standard, right, for all kind of surface bondings. And then this particle put it in the vial. And then we also make the iron silver, right? Silver is very good, for some of the environmental applications, right? And then so we have ion magnetic silver as another parts, so you can have dual functions. Okay, so technology I share with you is start from here. Is fundamental part is not my technology or not my invention. In terms of physics part, that is Nobel Prize in Physics 2007. So spintronic first discovery is 1988 by Professor Ferd and Professor Grunberg. So they found out that basically you have two magnetic layers sandwiched with non-magnetic layers now, and then you pass the current through that. If you can control these two magnetic layers with different magnetization configurations, means, for example, for this case, the high resistance is anti-parallel, makes this opposite to this, makes the parallel, you will have the low resistance. Means the first time you can connect magnetic behavior with electrical behavior. And the electrical is easy, right? So everything, once you involve the electrical, means not like optical. You can make small, you can make it cheap, right? Low cost, you can make it compact, right? You can make multiple sensors, right? Okay, so that's the beautiful for this discovery. So basically now the magnetic configuration can be integrated with electrical behaviors. And now the question to you just is, if this one is sensitive enough, or in terms of physics, and then you can using another field. That field can come from the nanoparticles. Magnetic particle can tip this one of the magnetizations here, configurations, and then you can change the resistance. So now means you can have the chance to detect very tiny field, right? And then with a very convenient way. So here's the idea. You can detect the molecules. So you have these sandwich structures. You print, for example, antibody on top of sensors, and then you pass through the current, right? And then you can have one configuration at one time, and then you have resistant values, okay? Now, if you have a magnetic particle on top, and then magnetic particle generated field can change the magnetization configuration. Not completely, but the tip a little bit, and then you can have the resistance value change. Now you can read out. And then another part is we just take advantage from standard amino acid. Right? For mercury detection, we not use that. We use the DNA. I will share with you. But for just explanation, so you're just using standard amino acids, and then you start with antibody. You put the antigen here, and then you have another detection antibodies. You have sandwich structure. I ignore that detection antibody, but you should have that one for sandwich. But for computation-based, you don't need to have that one. But in summary, basically you can build up these specific bondings, and then you can see the particle, means you can see the antigen. So it's very sensitive. And then you put together what's the advantage. You can have a high sensitivity, that's no doubt, because of this physics. And then you can have a matrix incentive. This is very critical, because once you detect the dirty waters, that's a lot of other parts, right? You don't want to see. And then you may influence your detection results, right? So if you use an optical, the laser beam may not penetrate through if you have different concentrations of some other things you don't want to see, right? However, for this case, for magnetic sensing, it's beautiful. And anything in between, as long as the specific bonding is okay, other parts, you will not see that. I just see my particles. Okay. So this is very critical. This makes this technology really fit to environmental monitoring very well. It's called the matrix incentive. And very fast, couple minutes, low cost, because this technology already been used in the hard disk drive, and for the read sensor in hard disk drive, and then you can have 8-inch wafer, make tons of the sensors out of the 8-inch wafer. And multiplex, that's another advantage. It means this sensor is very, very small, could be just small 100 nanometer or several hundred nanometers, and then you look at one areas like 3 millimeter by 3 millimeter region, you can hold 1,000 such sensors. If one sensor you print with one capture antibody, you can target on one antigen, means you can target on 1,000 different antigen at one time, just at 3 millimeter region. Okay. And then low volume detection, that's also very sure, right? You just don't need that much samples. For valuable samples, you can do this. Okay, so this couple of schematic drawing just show you, right? This already show you, and this show the we call the multiplex. So you have individual sensor. Each of the sensor you print with different capture antibody. For this case, also can be the DNA, right? So and then you can target on the different molecules, and then you can fabricate this one using nanotechnology in the clean rooms. And this I will skip. Now to come to the particle, and then we also can make the particles with high moment. And then the reason we can make this detection, one reason is before people using iron oxide particle. Now we suggest using iron cobalt, so you can have a huge moment compared to iron oxide. This commercialized. So this is the one I mentioned. That's a company started from Minnesota, tried to commercialize. And then moment at the low field one is 16 times difference. And this wafer, you start from wafer. In my lab, we can make a 4-inch wafer, 6-inch wafer, and then you make multiple chips. This is one chip, and the 60 millimeter, this 4-inch wafer, 60 millimeter, and then you can have 3 millimeter region. You can have a 64 sensor for this case. Okay. This real one, and then this 60 millimeter, and this 9 millimeter, and the reaction wall here, right? And size 9 millimeter, height 3 to 5 millimeters, and you put a droplet of, for example, Lake Minnetonka water. We did that, so data I will show you this from Lake Minnetonka. And then you can do the detection. And then this holder, yeah, here we have a Minnesota logo, and then plug in. So we have technique can print different molecular on the sensor, like capture antibody as example, try to capture different molecules. For DNA-based one, you can print different DNA strains on top sensor. And then this real signal, this is time, this is a signal, and this is a kind of interleukin 6 one, and we can detect with the time. You can see how the signal change with the time. Or you can see the average too, 0.1 picogram to milliliter to 20 nanogram milliliter at a wide range. So, yeah, this is real. So this is sensor zoom in after finish. So the 50 micrometer. This is one of the sensor. Many 100 nanometer wires here. Let's connect together. This is one of that, right? 500 nanometers, and then this with the particle. And then we detect this, for example, this one of the molecule of proteins, PAPP, that's heart attack molecule, the biomarkers, and then we work with R&D system, just is a neighbor of our universities, right? So we can do all kind of concentration detections, and then refer to that well. We do the multiplex, and then calibrate with their commercial available multiplex. They sell that, and using our technology compared to this different markers. This one, and this one, and then with different concentration, we detect them at one time. Okay. And then this technique I just mentioned, so it's a matrix incentive. No matter what you have, a lot of big, small molecular around, but they not influence your testing results. It's almost same and fast. And then, there's a couple of other features, repeatability over here. So this we published a while ago using the interleukin 6 as example. Professor Chen Guoxing from medicinal chemistry department is my key collaborator on this works at that time. And also we detect the urine, unprocessed human urine in terms of one of the small molecular that's called endoglin for the different group of the peoples, the 15 samples, and really successfully show the low risk, no risk, low risk, and high risk. So this Professor Xing, Professor Slayton work with me on this. Now, Mercury. Okay, so Mercury, I mentioned there's a couple of technology can do this, but it's big, I mean, the error bar is relatively large. And recently, there is one good progress. And the people found out, I think there's a couple of papers, and start from here. Not many people pay attention to this, but this, I believe, is a very important fundamental finding. And what they found out here is a mercury ion is specifically bound to this T base for this DNA strain. So you have AGCT, right? And then mercury ion specifically bound to that. And then they did show the experiment evidence and prove that. And then also using fluorescence technology, I just show you that's traditional way people do this mercury detections. And then using this kind of specific bonding, they also show that also works. Okay. Okay, so far you have traditional techniques, and here is something new discovery in terms of how you can detect the mercury, right, in terms of specific bondings. So we build up our detection right on top of this. Okay, here is the example just show. So mercury specific bond to the T-base. And then we print, right, the DNA string on our sensors. So we have control sensors, and then we have immobilized DNA, the DNA on the top of this sensor. We call it detection sensors, right? And then we have strep labeled magnetic nanoparticles, right? And then we have a detection DNA string. So that one, you have the biotin linked as the end, right? And also you have a T base, and then basically you have T base on this one too. So you have a mercury ion linked to this, and then now you have another T base from detection DNA linked to your mercury ion, and then you have for that specific DNA strain, you have the biotin. Now I have a particle just put in. The particle function with strep. Now I have a particle being specific bonding there. Everything finished, right? Okay, so this paper is under review. I think it will be show up very soon. This I would like to see this technology, the ROE, our NE the support. Yeah, so we did show good results. This real-time detection with this control, with different concentration of mercury ions, right? And it's the signals, it's the electrical signal we read out directly. It's very beautiful, right? And then you plot this one at the saturation region, right? This is minutes, and then you can see a chart. It's really it's kind of like a dose response curve, right? You can calibrate your testing setup. And then the detect nature water. This water we come out from my student drive to the Lake Minnetonka and got waters, and then we try to detect mercuries with different. Not this one. I think one of that is mercury ion concentration. Yeah, it is. Yeah, and then we try to dilute that one. Okay, with different dilutions, we can see the set of the data start from 10 nanomolar all the way up to the 10 micro. Yeah. Okay, so summary. I think I should stop here, right? So the summary you can see here is kind of a nanomagnetic technology for environmental application. I think I try to share with you. There's a very good possibility we can do that, right, based on what we developed. And there's a couple of things I would like you to remember. So for example, the sensitivity for the technique we have is zemtomol. So we can detect 150 molecular per sensor area. At room temperature, no fancy big setup, just a handheld, right? So that's the key. The sensitivity is the key. Recently, University of Minnesota will have another startup company just based on this technology, so called the Zepto Life Technology. The name comes from Zepto here. Yeah. And specifically about mercury detections, I list on here. So that's already shared with you. I will not read through this one. I would like to thank you very much, and then let's see. Okay, here. So I went through this chart with you, but I didn't show the system we have here. This is a real picture of our benchtop system. The dimension here is this 11 centimeter, this 18 centimeter, this height is 16.5 centimeters. Okay. This is our handheld one. We haven't fully packaged, but we are going to have a 3D printing frame to put our PCB inside, something like my hand size. So that's another one. And the particle we made in our lab, and the printing in the lab, and the sensor wafer made in lab, and we make these sensors in the clean room. We have clean room in Keller Hall. So basically, we can do everything there. And then we collaborate with different professors in the different departments on different projects in terms of the functionalizations and different biomarkers. And for example, I work with a lot of discussion with Professor Randy Singer and on the potential application for this technology for water detections. So a lot of good students graduate from past few years, and some students ongoing, and on the particle part, sensor part, and some of the fellows. For example, I have a fellow from medicine and chemistry department. Like Lina is one of the key now, is working on this sensing. So a lot of data collected by her, and he now joined the Nanjing University. So he returned Nanjing University. He is a part of that environmental department, something like that. He also tried to promote the technology there to see could help people there. A lot of collaborators across different departments. So really thank them. I will not read the name, but really appreciate that. Okay. Thank you very much.